All right, let's talk about something that trips up a ton of developers, even experienced ones: PostgreSQL transaction isolation levels. If you've ever found yourself staring at your screen wondering why your data literally changed in the middle of a single operation, you are in exactly the right place.
You've seen these terms, right? Read committed, repeatable read, serializable. They're everywhere, in the docs, in pull requests, in those late-night debugging sessions. But knowing the names is one thing. Knowing which one to reach for and when to make sure your app's data stays correct, well, that's the million-dollar question. And that's exactly what we're going to clear up today.
So, at its heart, what even is transaction isolation? It's really all about controlling chaos. Just imagine you and your buddy are both editing the same Google Sheet at the same time. Isolation levels are kind of like the rules that decide if you see their changes character by character or only after they hit enter, or maybe not at all until you manually refresh. It's all about managing what everyone sees and preventing things from getting messy.
To really get to the bottom of this, we're going to walk through it step by step. We'll start with the basics and build our way up to a simple set of rules you can literally use every single day.
First, we'll tackle the default, read committed, and see where it falls short. Then we'll climb the ladder to repeatable read and serializable and figure out what problems they solve. After that, we'll boil it all down into a simple rulebook, your new SOP. And we'll finish up with some real-world examples to make it all click. Let's start with the absolute workhorse of Postgres, read committed. This is the one your app is almost certainly using right now, probably without you even thinking about it. So it's super important to understand exactly how it behaves. Okay, so read committed is the default for a good reason. It's fast, and it gives you one huge guarantee: you'll never see dirty data. That means you won't see changes from some other transaction that hasn't been officially saved yet. But here is the key, the absolute most important thing to get. Each individual statement in your transaction gets its own brand new snapshot of the database. It sees the world as it was the microsecond that one query kicked off.
That sounds pretty reasonable, doesn't it? No dirty data? Great. But that snapshot per statement thing has a really interesting side effect. What do you think happens if you run the exact same query twice inside the same transaction?
Let's play this out. Your transaction kicks off, and the first thing you do is check a user's account balance. The query runs, it gets its little snapshot of the database, and it comes back saying the balance is $500. Easy enough.
But before you do anything else, another transaction from somewhere else in the system successfully withdraws $100 from that same account and commits its work. Now, back in your transaction, you run the exact same select query again. Because read committed takes a new snapshot for every single statement, this second query sees that new reality. The result is now $400. This little surprise is called a non-repeatable read, and it can cause some really subtle and frustrating bugs.
Now here's the twist. For a massive number of situations, this behavior is totally fine. In fact, it's optimal. If you can write your logic into a single atomic statement, like updating an inventory count and checking that it's above 0 all at once, the database handles all the locking and consistency for you. In those cases, read committed is fast, it's efficient, and it's perfectly correct.
But what if your logic is more complicated? What if it can't be squished into one line of SQL? What if you absolutely need a stable, unchanging view of the data for your whole transaction? Well, that brings us to the next level up the ladder, repeatable read.
Repeatable read solves the exact problem we just saw. Instead of taking a snapshot for every statement, it takes one big snapshot the moment the entire transaction begins. Now, if you run that select balance query 10 times, you're going to get $500 every single time, no matter what other transactions are doing. It makes your reads, well, repeatable.
Awesome. Problem solved, right? Let's just use repeatable read for everything and call it a day. Not so fast. While it's fantastic for things like reporting, it hides a really sneaky and dangerous trap when it comes to writing data.
And here it is. This is the big one that catches so many people off guard. Repeatable read is vulnerable to a nasty little thing called a serialization anomaly, but you'll usually hear it called write skew.
So what on earth is write skew? Imagine you have a business rule that says there must always be at least one doctor on call. Now, two doctors in two separate transactions both check the system. They both see there are two doctors on call. So, based on that info, they both independently decide, hey, it's safe for me to go off call, and they both update their status. Both of their transactions commit successfully, and the result? You now have 0 doctors on call. The business rule is broken, even though neither transaction did anything wrong on its own.
That's right skew.
To defeat this final boss of concurrency problems, we need to bring out the big guns. We need the highest, most protective isolation level that PostgreSQL has to offer. Welcome to the fortress, serializable.
Serializable is the ultimate promise. It guarantees that no matter how many transactions you run at the same time, the final result will be identical to as if they had all run one at a time in some nice orderly line. It makes that on-call doctor scenario logically impossible.
And this is its superpower. It prevents everything. Dirty reads? Gone. Non-repeatable reads? Of course. Phantom reads? Or new rows just pop into existence mid-transaction? Nope. And most importantly, that tricky, dangerous right skew? Completely eliminated. It gives you true mathematical proof-level data integrity.
So how does it pull this off? This is the really clever part. It doesn't just lock everything down and grind your system to a halt. Instead, Postgres watches the transactions like a hawk. In our doctor example, when that second doctor tries to commit, Postgres sees that this would create a result that's impossible in any one-at-a-time ordering. So it says, nope. It aborts one of the transactions and throws an error, which tells your application code, hey, you need to try this whole thing over again. Okay, deep breath. That was a lot of theory. But how do you actually apply this in the real world without giving yourself a headache every time? Let's build a simple, standard operating procedure.
Here it is, just 3 simple questions. First, can I enforce my business rule in a single atomic SQL statement? If the answer is yes, great, stick with the default, read committed. Second, is my rule more complex? Does it span multiple rows, or maybe depend on the absence of certain rows? If yes, you need the safety of serializable. Just go for it. And finally, number 3, is this job mostly just reading data for a report or some analytics? If you just need a stable picture, repeatable read is your best friend.
And this all boils down to one golden rule. Don't just crank the dial to the highest level because it feels safer. Stronger isolation levels have performance costs, especially serializable, which can cause transaction retries. The goal is always to pick the most lenient, highest performing level that still guarantees your application is correct.
Okay, let's wrap this up by looking at how this SOP maps to some common systems you might actually be building. This should really bring it all home.
Think about a ticket booking or inventory system. It's high throughput, and you can usually use atomic updates. Read committed is perfect there. What about analytics dashboards? You're pulling data for a big report and need it to be consistent from start to finish. That's a textbook case for repeatable read. But at payments ledger, a financial closing process, there is absolutely zero room for error. The data must be correct, that is non-negotiable, and that's why you use serializable.
So, here's the final thought I want to leave you with. The default is the default for a reason. It's often the right choice, but it is not always the right choice. The next time you're designing a feature with complex logic, just take a moment to run through those 3 questions. Your app is almost certainly using read committed right now. And after today, you now have the tools to ask, is it the correct one?